In this video, we're going to start looking at calculus and begin with differentiation. Calculus is a study of change, and differentiation is a procedure used to find the instantaneous rate of change. So what does that mean? Well, essentially we're looking at how one quantity changes in response to another. Let's start off with a scenario that you've probably met before. What I'm going to do here is define three different quantities. The first one, S, is going to be the displacement, and that will be in meters. So displacement. The second one is going to be T, that's going to be time, and we will have that in seconds. And the third one is going to be the velocity, and that will be meters per second. We've seen from previous work that if we have S over T, that's going to be equal to V. Displacement over time is velocity, or if you like, distance divided by time is speed. We're fairly happy to accept that. This is what we call the rate of change. So the rate of change is velocity. If we went ahead and did this on a graph, we would have now the vertical axis, and on the vertical axis we will put the displacement in meters. So let's do that. Let's put now S, and that's going to be meters, and then we're going to have now T, and that will be in seconds. Let's draw now a linear function. So we could say now, technically, that displacement is a function of time. So this is a straight line. So we can see that we've got a constant gradient. If I put some points on here, let's say that's 1, 2. So we've got 1 second, 2 meters. Let's put another one on, let's say 2, 4, 2 seconds, 4 meters. Then we'd have 3, 6. The velocity now is the gradient of this line, or the rate of change. So if we pick 2 points, we could do now 2, 4 and 1, 2. The gradient will be 4 minus 2 over 2 minus 1, which is going to give us now 2, or more specifically in this case, 2 meters per second. That is the velocity. If we were dealing with this in terms of the derivative, which is what we get when we differentiate a function, we would say now ds dt. The rate of change of displacement with respect to time is given to be velocity. And this now gives us the form if we were dealing with calculus, the derivative. If we differentiate displacement with respect to time, we get velocity. We often call this the gradient function. Okay, let's go one step further and look at another example. Let's take a different scenario, and what I'm going to have this time is a different particle or some different object moving. And let's go ahead and do this. Let's do this one right here. What I'm going to have this time is velocity. So we've got velocity, and that will be v meters per second. And then now we've got t, and that's going to be seconds. So this is a velocity time graph. If we pick a point right here, so we're starting again at 0, let's say we've got 1, 6, and then we have this point right here, which is 2, 12, and then we have 3, 18. Let's look now at the rate of change, or the gradient of this particular line. Again, we can see now this is a straight line, so we've got a constant gradient. We're looking this time at v over t. Now, v over t will give us the acceleration. So if we're looking at the gradient of this line in anything such as physics that we might have done, or any form of science that you may have done lower down the school, velocity over time, or the gradient of this line, is acceleration. If we were doing this now in terms of the derivative, we would say dv dt is equal to a. The derivative now, we're differentiating velocity with respect to time, and we get acceleration. So this is the gradient function. So if we look right here, let's pick 2 points. I mean, we can start here if we like. It's entirely up to us. We've got now 12 minus 6 over 2 minus 1, and that's going to give us 6. And in this particular case, meters per second, or meters per second squared. So now we have our derivative, which is the gradient at any given point on this graph, which in this case is acceleration. So if we differentiate once, we get velocity. If we differentiate again, we get acceleration. Now, this moves us on to the idea of the derivative. So whenever you're talking about differentiating a function, you're looking to find the derivative, which is the gradient function. Both of these examples have been now linear functions. So they're straight lines with constant values. Variables are not always related in a linear way. So let's say now we had our ST graph, and this, instead of being a straight line, was a parabola. So let's go ahead and just sketch this up. So let's go ahead now and draw a parabola instead. Let's say that S, now the displacement, S was equal to t squared. So we're going to start at 0, so we'll only have the positive part of the parabola, so this now is S is equal to t squared. So we've got now S, which is going to be now the displacement in meters, and we're going to have now t, which is the time in seconds. If we consider now, what we're looking to do is find the gradient of the tangent at any given point. So if we first think about a tangent now is a straight line that is going to touch this curve. So if we take this point right here, this point, let's just say that this is 1, 1. So if we've got t is equal to 1, s is going to be equal to 1. If t is equal to 2, s is going to be 4. If t is equal to 3, s is going to be 9. So let's take another point on here, and let's now look at the gradient of the curve at this point right here. Now if I do that one, we've got a tangent, and it's not massively accurate, but it'll give you some idea. That's just going to touch right here. We can see that the gradient is changing with this curve. If I picked another point right here, let's go ahead and pick another one, we can see now that this is really quite steep at this point. So let's put one just there. So what we have is something looking like that. So as time is increasing, we can see that the rate of change for this particular graph is also increasing. And that's really important. As stated, variables are often not related in a linear way. We can see that this now gives us a quadratic. We might have a cubic. We might have some trig function. So it's not always the case that we're looking at a straight line. In this video, what we're going to do is look at finding the derivative, which is the rate of change or the gradient function for a range of simple curves. We're going to look at this from first principles. Now, first principles initially seems quite daunting, but does really give you an insight of what's going on. What I'm going to do here is just leave you to think about something now. If I wanted for this particular function, so displacement is a function of time, y is equal to x squared, y is a function of x. Generally speaking, we'll use this to begin with, y and x. I've only used s and t because it gives us some visual representation or something that we can at least do. Now, if y is equal to x squared, the derivative, which we're going to call dy by dx, is going to be equal to 2x. And later on, I'm going to explain why that is the case. If s is equal to t squared, ds dt, the rate of change of displacement with respect to time, which is velocity, is 2t. So that gives us now the gradient of the tangent at any given point. So we're looking at the instantaneous rate of change for any value of t. So when you hear the word derivative, differentiate, gradient function, rate of change, this all comes back to the same thing. So let's start off now with differentiation from first principles. I'm going to look at this in a couple of different ways. You're going to meet two different types of notation. You're going to meet Leibniz notation, which was named after a mathematician, and you're going to meet function notation. So let's start off now with Leibniz notation. So if y is a function of x, the derivative dy by dx is given now to be the gradient function. So if y is equal to a function of x, the first derivative is dy by dx. So this is Leibniz notation. We could find the second, the third, the fourth derivative as well. If we have now f of x, the derivative using function notation, so the first derivative is f dash of x. So on the left, we've got Leibniz notation, and then on the right, we got function notation. To show differentiation from first principles, it's easier to use function notation. If you do want to read up using the Leibniz notation, it's entirely up to you. I'm just going to go with the easier one so you can kind of get your head around it. Okay, so what we're going to do then is start now with a graph. And I'm going to have a graph. It's going to be some function of x. And I'm going to make this slightly easier by defining now the f of x to be x squared, as we can get some idea of what's going on. So this is a simple curve. So the f of x is equal to x squared. I'm just going to take the positive part right here, and it will look something like so. So we've got this, and it'll look, give or take, like so. So what we have now here is x, and then we have y. Okay, let's take some point on here. Let's just take this point right here. And what we're going to have is an x coordinate, and then as a result, we will have now the f of x. So let's say x was equal to, 2. Then what we could say then is the f of 2 is going to be equal to 4. So all I've done is evaluated the function at 2. So x, f of x. Let's now increase this distance of the x coordinate by some small amount, and that small amount is going to be h. If you were dealing with the Leibniz notation, this would be some small quantity called delta x. So delta x, delta is just a small amount, it's an increase in the x coordinate. So this distance right here that I'm doing is going to be some distance, and I'll put it just here. If this is going to be x, then we're going to have this point right here, and this is going to be x plus h. So it's some small quantity. So at this point right here, we have x plus h. So let's say h was 1. This point right now would be 3. Then we would have now the f of x plus h. So let's just say, for example, now h was equal to 1. This would be x would be equal to 3, and then the f of 3 would be equal to 9. I'm just doing this now more formally. So we've got x, f of x plus h, f of x plus h. At this point, what I'm going to draw is a secant line. A secant line is just now a line through these 2 points. And initially, this is going to give us a crude approximation to the gradient of the tangent at this point right here. Quite clearly, that's not a brilliant estimate. As we decrease the value of h, and ultimately we say as h tends to 0, so as h gets very small, this approximation is going to get better. So what we're going to do now is decrease h. So if I halved h, let's say I now put it just here. So I'm now going to get this point right here, and if I drew now the secant line through these 2 points, we got a slightly better approximation of the gradient of the tangent at a given point. So if I just put that through there, that looks a bit better. Now ultimately what we're trying to do is get the gradient of the secant to match the gradient of the tangent. Now if I look at the gradient of the tangent at that point right here, what we're going to have is something that looks a bit like that. So you can see now as I'm decreasing the value of h, as h tends to 0, and h is this tiny amount, delta x is a tiny amount. What we're going to get now is a better and a better approximation to the gradient of the tangent on this curve at any given point, and that is the derivative, that is the rate of change. So if we now look at the gradient of the secant, and this is the gradient of the secant, which I'm just going to call m. The gradient of the secant now is going to be the change in y over the change in x. So we're going to get the f of x plus h minus the f of x. So the f of x, and then this will be over the change in x. Change in y over the change in x. So this is going to be x plus h minus x. So we can say that the gradient of the secant will be the f of x plus h minus the f of x all over h. So remember, the secant is just this line going through the 2 points, but what we want is now the tangent where it just touches this point and gives us the instantaneous rate of change at any point on this particular curve. Now, at this stage, we're going to consider what we call a limit. So when we're talking about a limit, we're talking about getting very close to a particular value. And what we now say is the derivative, the gradient function, so the gradient of the tangent at any given point, which is f dashed of x, is now the limit as h tends to 0 of this quantity right here. So we've got now the f of x plus h minus the f of x all over h. And this now is the definition of the derivative, and we found this from first principles. So if you're asked to show the derivative from first principles, essentially you're looking at the gradient of this secant tending to, the value of h tending to 0, thus giving us now the gradient of the tangent at this point, which is the derivative, which is f dashed of x. And we define it in this way. In the same way, you might have had dy by dx as the limit of delta x tends to 0 of, and then we'd have now, in here, we would have our values of x plus delta x all over delta x. H is just easier than delta x. But again, in later videos, I may go and actually use delta x. I just find this notation far more manageable. So let's think about this now. Where does this all fit in? Well, what I'm going to do is give you a standard result. In this particular chapter, we're going to look at differentiating polynomials. So a polynomial would be, for example, 2x squared plus 4x plus 1. It might be 3x cubed minus 6x squared plus x plus 8. So a polynomial, we're looking at powers of x. So let's look at a polynomial. Let's say we've got y is equal to x to the fourth plus 3x squared plus 2x plus 1. So in this particular case, we all have now positive values, so we've got integer values of x, and we could find the derivative. Now, generally speaking, if y is equal to x to the power of n, the derivative dy by dx, the gradient function, will be nx to the n minus 1. And this is a very formulaic way of looking at it. Quite clearly, we can't constantly do this for all functions. Now, many functions we can differentiate. So later in the chapter or in the topic, we're going to look at differentiating trig functions. We might look at differentiating log functions, and that comes later in the course. But for now, we're going to be differentiating polynomials. If we have a polynomial, y is equal to x to the n, so x squared, for example, then the derivative, we multiply down by the power and drop the power by 1. If you like, if f of x, the original function, is x to the n, then the first derivative, f dashed of x, will be nx to the n minus 1. So, let's think about now what I said before. When we looked now at the derivative, and if we go back here, if y is equal to x squared, dy by dx is equal to 2x. And we saw now, we've multiplied down by the power, and we've dropped the power by 1. Okay, so does this work? Well, let's have a look at this in the context now of x squared. So what I'm going to do is the following. If we take the f of x, let's take the f of x to be equal to x squared. Now, our definition is the f dashed of x will be equal as the limit now of h tends to 0 of x plus h, f of x plus h, let's put that in, the f of x plus h minus the f of x, and then that's all going to be over h. So this is what we've just defined here. So all we've got now is the f of x plus h minus the f of x over h. Let's look at applying that to x squared. So what we're going to have then is the following. We've got now the f of x is x squared. So this is going to be x plus h all squared minus x squared. So all I'm doing in this particular case is applying our particular definition of the derivative, the gradient function, and using x squared. And that's all going to be over h. Let's now expand this out. We're going to get x squared plus 2hx plus h squared minus x squared. That's what we're going to have in the numerator. So expanding the double brackets, x squared plus 2hx plus h squared minus x squared all over h. Now at this stage we can cancel the x squareds. That's going to give me 2hx, so 2hx plus h squared over h. At this stage now I can divide through by h. So that's going to give me 2x plus h over 1. Now we said that the derivative was now as the limit of h tends to 0. So that value of h gets incredibly small. It tends to 0, it won't be 0 as we can't divide by 0, but it will get very close. So that's now the limit that we have. Now if we consider that this is going to now, let's just write this here, h is going to tend to 0, that now leaves us with 2x. So we can say that f dashed of x will be equal to 2x. And that stacks up with exactly what we found before. So we wouldn't use this. This is laborious. You wouldn't be expected to do this time and time again. It's just showing now from first principles the result is exactly the same. So for example now if we said the f of x was equal to x squared, we know that the derivative is going to be f dashed of x. We multiply down by the power and then we drop the power by 1. And of course you just write that as 2x. So let's have a look at x cubed. If we say now the f of x is equal to x cubed, what are we expecting to be the derivative? Well, f dashed of x from this point should be 3x squared. So let's see if that's the case. What we're going to do is apply this. So let's define now the f of x to be equal to x cubed. So what we want then is the f, so let's write f dashed of x. What we'll have now is the following. This will be as now the limit of h tends to 0, we will have now the following. We will have x plus h, which we're going to cube, minus x cubed. So this time I've now used x cubed instead of x squared all over h. In terms of expanding x plus h cubed, you might want to do that manually. I'm going to kind of half cheat and use the binomial expansion. You'll meet the binomial expansion in a later video. We're going to get now x cubed plus 3x squared h plus 3x h squared plus h cubed. So if you go ahead and expand that, that's what you're going to get. Okay, minus now x cubed, that's the numerator. That's all going to be over h. So let's go ahead, cancel these off. They're now cancelled. We can divide through by h, so we're going to get 3x squared plus 3xh plus h squared. Now consider as h tends to 0, what's going to happen to this right here? Well, that's going to tend to 0 and that will as well. So we end up now with f dashed of x being equal to 3x squared. And that exactly stacks up what we expected to do. We know that if we have the f of x, so the f of x is equal to x to the n, the derivative f dashed of x will be equal to nx to the n minus 1. So when you're differentiating polynomials, you don't go through this rigmarole each time, you just use a standard result. I think it's massively important though to get some understanding of what the derivative is from first principles, rather than just seeing this as a sort of plug and chug formulaic approach. Okay, so let's actually go ahead and do some. So let's say we've got now y is equal to, let's go for 3x to the 4th plus, let's go for 2x cubed plus 5x squared minus, let's go for 2x plus 4. So what we're looking for then is the gradient function, the first derivative. Now the first derivative is dy by dx. If I wanted the second, d2y by dx squared. So if we go way back to my first example, when we had now, we had ds dt was equal to v. If we differentiated this again, d2s by dt squared would give us the acceleration. So we can differentiate twice. In this particular case, we can certainly differentiate twice. So let's go ahead and do this. Let's take the first derivative. So we're going to get 12, multiply down by the power, drop the power by 1. When you're doing this in an exam, initially you'll have to show 4 workings. So in the first few times, you expect to put 4 times by 3. Do check with your exam board or teacher what they expect, because quite clearly it's quite tedious after a while. Multiply down by the power 6x and drop the power by 1. Multiply down by the power 10x, drop the power by 1. Okay, now at this stage we've got a little 1 here. So I'm going to have minus 2, so I multiply down by the power, and I'm going to drop the power by 1. If we consider now a couple of different ways to think about this, this is x to the 0. So if this is a polynomial, we've got now our descending powers of x. As soon as I multiply down by the 0, I'm going to end up with 0. So if we just tidy this up, we've got 12x cubed plus 6x squared plus 10x minus 2, and that is the first derivative. So you can see that I've not put that through the long-winded formula. I've just now used the property. If we got y is equal to x to the n, where x to the n is a polynomial, differentiate it, multiply down by the power and drop the power by 1. Now, why did this turn to 0? Well, there's a couple of ways you can think about it. Formulaically, you can just think, well, x to the 0, you multiply down, you're going to get 0. But let's look at this in a slightly more well, in-depth way, I'd say, or a slightly more logical way. If y is equal to a constant, let's say y is equal to 4, that's a straight line. what the derivative is the gradient function. If we look at that, what's the gradient of that line? Well, the change in y over the change in x is naught. So if we wanted now the derivative, which is the gradient of that line is naught. We can see the rise over the run, the change in y over the change in x, delta y by delta x, in this particular case is going, or dy by dx in this particular case, we got naught. So if we differentiate a constant, we're going to end up with naught. Now if you think about this right here, if we differentiate a straight line, we're going to end up now, let's just write this, let's say that this is going to be equal to, let's say y is equal to 2x. If we differentiate this, what we're going to get now is dy by dx is going to be equal to 2. And that kind of tallies because it's 2 all the way along. Yet if we think about differentiating a quadratic, let's say y is equal to 3x squared, then the derivative dy by dx, or f dash of x, is 6x. Now, if we think about this, what we're going to have is different values of the gradient at that point. So let's just jot now, let's draw a quick sketch of it. So let's say we had 3x squared. Now this is going to give me 6x, which is going to be a straight line. So let's just go ahead and do that. That's 6x. Now if we look at that at the given point right here, let's say now this point right here, if that's where x is 1 and y is going to be equal to 3, let's think about the gradient. Well, it's going to be 6 times 1, so m at this stage is going to be 6. But if I took this point right here, where we've got 2 and then we're going to have 12, well, the gradient is going to be now 6 lots of 2. So we're going to end up with 12. So we can see that that gradient is altering with the curve. So that's going to give us something like that. So you can see now, the further this goes up, and quite clearly with this one, we're going to have negative values, because when we sub in our negative, we're going to have a negative gradient. In later videos, we'll study that a little more. But if we took this point right here, and we had the point now minus 1, then the gradient would be minus 6. In the same way, if we had one just here, we'd end up now with minus 12. So that gives you some idea. Let's just recap. When we're looking at calculus, we're looking at how things are changing. The derivative is the instantaneous rate of change. So if you differentiate a function, you get its derivative, dy by dx, or f dash of x. We're looking at how one quantity is changing with the other, and we're looking to find now the gradient of the tangent at any point on a curve. So there we go, differentiation from first principles. You can see now that it's quite laborious to go through it all, but we can use those standard results. And in later videos, we're going to use those standard results to write out the derivative of a function and evaluate it at any given point.